course on NPTEL as my college elective.
Okay.
And I had a doubt regarding the what do you call explosion models, like synchrotron explosion model, right?
Yeah,
Synchrotron
yeah.
show.
I am coming one by one. So I have already some list of questions. I will of course try to answer as much as possible. And just a minute, please hold on for a couple of minutes, because I don't know, like I can only see Aryan and Ayush Bidlan. Yeah, just please wait a little bit, and then
Sure.
yeah. I mean, I'm simply waiting because so that some of your friends can also make profit out of your question. Okay, so Monu Kumar, yeah. Okay. So of course, I will try to answer the questions first for the people who are present today, and then I will go to the questions listed in the forum. So. So, Mr. Krishnan, should we start at 7:05 like that? Is it okay?
Yeah, it is fine, sir. Absolutely fine, sir. But I stopped the broadcast in YouTube.
Okay. Yeah.
But you can officially start around 7:05, sir.
Okay. I mean, maybe. I mean, just wait a little bit.
Right, sir. Okay, sir.
Sure. Yeah, I can see other people are also joining. That's excellent. Last time I just saw 1 or 2 people. I mean, maybe 2, 3. But now new names are coming. Great to see. It would be great. I don't know whether it's possible to put their videos on so that I can see who are.
Yes, sir. Students, those who have a very good bandwidth can switch on the camera so that sir can also see you.
Yeah, it's always, like it's a pleasure to talk to you. Who is asking? Yeah.
Deepak, it will be great if you turn on your cameras. Sometimes because of the bandwidth, no sir, students tend to turn off.
No problem. That's not a problem. Just if it is possible, it's always, it's always easier when the student talks and I can see their expression, and when I explain something, then I can also understand whether they really understand or not.
Right, sir.
Yeah. Okay.
Participants, we encourage you all to turn on the camera just in case if you have a good bandwidth. Otherwise, it's not compulsory. Yeah, good. Sanket has also turned on the camera.
Yeah, I mean, this is totally, it's a personal request from my side. If you feel convenient, you can. Yeah.
Yes, sir.
Okay, so I think it's 7:05, so we can start both the broadcasting and the formal session if you want. I mean, I don't know, yeah. So, first of all, yeah. So, Mr. Krishnan, you want to start with telling something, or I directly?
Yes, sir. You can start, sir. You can directly start.
Okay. So I formally welcome all of you to the second live session of this course of Introduction to Astrophysical Fluid. I don't know how many of you are really from physics background and astrophysics background, but it's always, I mean, I am very much pretty happy to see people from diverse background and still they are getting attracted to astrophysics. And I mean, the main vision of this course is to really tell you what astrophysics really means, because sometimes we have various misconceptions. Sometimes we are mixing with astrophysics and astronomy, astrophysics with high energy astrophysics. So what in the premise of this course, what I am trying to explain is more like what is a normal, non-relativistic, non-high energy and like non-astronomy astrophysics. So this is a so-called, if you see it, we sometimes call it a spatial astrophysics. Okay, and sometimes people also have the idea that we will talk about the evolution of the stars. That is called the evolutionary astrophysics, or the temporal astrophysics. So here we are talking about spatial astrophysics. That means we are not really interested in the evolution, but let's say the things are there, they are getting formed, they are getting interacted, and they are getting studied. and they are getting studied only using the basic physics principles. Okay, so, and actually, if you see, these are non-relativistic classical mechanics till now. Okay, so that's also a very important point, that using very simplistic tool like this, we can try to explain most of the fundamentals. Now, in today's live session, I will try to answer one by one your questions. So let us first try to address Aryan's question. Aryan started to say something, then yeah. So Aryan, you can go on.
So my question was regarding the synchrotron shock model. So as we know, there are 4 stages, right? The first stage, the shock comes out, and the second stage, it goes undergoes a deceleration phase, which increases its cone size. Like there's a theta j, we call it the solid angle, and while decelerating, the cone angle it becomes larger than the geometric.
Just a minute, exactly which lecture and which topic you are talking, because I did not talk about this theta z thing in this. We talked about more like spherical explosion. Are you talking about supernova explosion or what?
This is actually what you call preface to the gamma ray burst and fast radio bursts, like originators or progenitors.
No, but I mean, was it included in my lectures? Because mostly I will try to explain what is the questions related to the lecture and the course, and then I will come to the peripheral questions. So do you
okay, sorry, this is this is not exactly.
So do you
from
have
the
a
lecture
question related to the lecture?
No, sir, not exactly. The
Okay,
lectures are very good. Yeah,
okay,
clearly understandable.
Okay, please wait, and let me first survey over all of your friends, so that some of them have some question really related to this lectures, because the lectures are also covering a lot of things. So Deepak Vambani, do you have any question related to the course and the lecture?
Not right now, sir.
Okay.
Because...
Okay. So any of you have a question related to the course and the lectures? Because the live sessions are targeted to complement the lectures. That means the points which are not clear during the lectures, then I will try to elucidate that in the live sessions. Yeah.
Hello, sir. I have a question.
Yeah.
Regarding odd limit. You were talking about in lecture 10.
Mm-hmm.
So we get a raw matter. Raw matter means density of matter in the galactic around the galaxy. So it is about 10 raised to around 10 raised to minus 24 gram per centimeter cube. So I have a wonder about, this is a very low density compared to we are already talking about. So my question, this is how it is very low density is there.
So exactly, I mean, one is that when we are talking about, so you are talking about the visible matter or the gravitating matter?
Total matter, which is gravitating.
There's a total gravitating matter. So you understand that the gravitating matter includes both the visible matter and the dark matter, right?
Yeah.
Okay.
Yeah.
And according to you, this is pretty low. So, and you are already wondering. So, so as you understand that the density of the visible matter is even lower. So you see that this is only because that most of the visible masses, they are very much concentrated into different parts, okay, and very small regions in space. Most of the interplanetary, interstellar, and intergalactic places are very dilute. Now, why it is like that? That is, most of the time, as if you really try to understand what is the nature of gravity. The nature of gravity, just very simplistic. Of course, your question is not a very simple one. Your question has many components, but in this how to say, like in the framework of this present course, what I can simply tell you with a simplistic assumption, what is the basic nature of gravity? Gravity attracts everything, correct? And when it attracts and the mass, certain amount of mass is compiled in a certain region, then basically the gravitating force towards it is actually increasing. Okay, so now what happens that after a certain amount of mass, the body is actually experiencing its self-gravity, which in general for normal Newtonian mechanics, we like, how to say, like we neglect for normal particles and for moderate masses. Okay, we say that particle A is actually attracting particle B and the particle B is attracting A. But when some amount of considerable amount of mass is compiled, then it is actually getting under self-gravity. And if you have already followed most of my lectures, I think you have also known about Jeans instability. Did you?
Yes, sir.
So if you know about this, so the property of gravity is like it makes always a collapsing, and collapsing means say inward collapse. So most of the mass always try to get collapsed in a very short region in space. And that's why finally you know that eventually we have very compact objects in astrophysics, starting from white dwarfs, neutron stars, and black holes, right? So that is because the intrinsic nature of gravity is attractive in nature. Okay.
Yes, sir.
So this is the simplest way to understand your question. And if let's say most of the particles, if let's say the gravity is not really very much important, okay, and then most of the cases what happens that this most of the cases where gravity is not important, the particles, they don't get compiled and they don't get concentrated, and the whole medium is actually stays like a very dilute medium of very low density. Clear?
Yes, sir. Yes. Get it.
Okay. Okay.
So
now
so,
why?
sir,
No, just a minute.
Go
So now why some parts is is really some part is really concentrated with respect to the other. That is because there are perturbations, there are many nonlinear phenomena like with turbulence and everything. So that can explain that those things.
okay, sir. So
yeah.
So, sir, here we talking about the gravitation. So, other forces can contribute into the matter like this. We have a total matter is luminous matter and plus dark matter is there. So, we can neglect we can consider other forces as well.
We don't know what dark matter is, but only we know that the only way they can interact is through gravity. That is just the observation. We really don't know what is there. So from what we observe by direct and indirect observation, of course, like the dark matters cannot be observed in a literary way. That means you cannot see. Okay. So yeah, but from the indirect estimates, what you can say that the only way they actually interact with themselves, and actually how they really interact with themselves is a question of active research. We really don't know very much, but at least for the only way to link, way of linking dark matter to normal visible matter is through gravity. That's the best we know till now. So so basically what we observe, in order to model that, we have to neglect the other forces. That's the answer.
Okay, sir, get it.
Okay, so in astrophysics, the problem is that in astrophysics, sometimes you really cannot really do whatever you want. You have to depend on some estimate, some observational data, and depending on that, you have to try to model consistently. Okay.
Yes. Yeah, sir. Sir, my next question is about steady disk. You taught us about the Pringle graph, Pringle 1981 graph. You know about that. Surface density versus R by R0 plot. So my
Yeah.
question is about what in here we want to study the evolution of accretion disk. So what in here we at the x-axis we chosen r by r0. So
Mhm.
my question is about what is r0 is there. So I cannot get that. You
Oh,
said
no. That is, I think, just a minute. Let me, if I understand your question, this is not a very difficult one. Let me just search for this point, and then this is right. And then I think in this, everything is done, right? Yeah, right. So, I mean, if you, do you have the lecture notes with you, right?
yeah I have, but
Yeah,
I
yeah. No. So
also
I mean,
have.
so R0 is something. It's called a reference line. So according to whenever we try to analytically describe the dispersion of, or the spreading of an accretion disk right from a ring. So the initial position of the ring with respect to the central mass is given by R is equal to R0. So that is the initial position of the one-dimensional ring.
Okay.
Okay.
Okay. So get it. And okay. Thank you, sir.
Exactly. So exactly at t is equal to 0, at r is equal to r0, you have this Dirac delta type of thing.
Yeah. Dirac delta r minus r0.
R minus r.
Yeah. Okay.
Okay. Any other question related to the lecture, related to the science? If yes, you can go on. Otherwise, what I will do, I will try to explain one by one the best possible way, in the best possible way, the questions which were asked in the forum. So I am going one by one. Okay. So Sumit Banerjee asked me a lot of questions. Sumit is absent today, so I thought he would be there. But anyways, so he asked me that. I mean, in some lecture, he said that he thought that friction is basically is responsible for the development of a velocity gradient. And then he thought that when I would expect friction to act on the layers and slow down, thus building up a velocity gradient, the layer touching the surface will experience higher friction, which will gradually decrease as we move away from the surface of contact, thus creating a gradient. So Sumit, as I told you in the mail, that this concept is not correct. So of course, frictional force, gets developed as a reply or response from the fluid due to a velocity gradient which has already been developed by some external effect. That means, for example, if I exert shearing stress to the uppermost layer of a fluid, then you can see, and if the fluid is actually forced to stay on the floor, then of course there should be a non-zero velocity gradient. Now then the fluid will try to respond to this perturbation or external shear stress in terms of this frictional stress. Now, whenever a system tries to reply, and then the system actually tries to, what is the meaning of replying? That means the system tries to kill the cause. That means that now what the viscous force will do, the viscous force will try to kill the velocity gradient between the layers by the transfer of linear momentum. And that's why whenever what you are thinking that the whole fluid becomes at rest with non-zero velocity gradient, that is not possible. That you can easily understand. If there is a non-zero velocity gradient, then the whole fluid cannot be at rest. Okay, if the whole fluid at rest, then at every layer the velocity should be 0. That means the relative velocity is 0. So basically, for a very high frictional drag, the state of rest is achieved, thereby just vanishing the whole velocity gradient. Okay, so that is one question. Then another question is, okay, you said that is the viscosity and the friction, this is the same thing? Yes, as I said. So friction is a common term which you learned during your Newtonian mechanics class. For fluid, we say, so this was a dissipative type of force. For a fluid, we also model some dissipation in terms of viscosity. So qualitatively, you can always think that friction is, something very much, viscosity is something very much analogous to friction. Of course, the way of treatment will be different, because there we were talking about the motion of one particle, and here we are talking about the motion of motion in a continuum. So you see, like, and if you are not taking a Lagrangian point of view, you are simply taking a Eulerian point of view, of course, then you have to wisely treat these things. Okay, so then you have to say that at every point in space, you have some dissipative effect associated to that point. Okay. So this is what it is. Then another good question, I think this is also will be interesting for most of you. That is, rigid body rotation of fluid sounds like an idealistic case, but is it really correct? In reality, however, I would expect differential rotation. So why are we at all worried about Newton's hypothesis not holding in such cases? So for all of you who are following this course, believe me, actually, in many instances in astrophysics, basically what we observe is something very close to rigid body rotation. And actually, it is practically difficult to see differential rotation prominently. But for example, in sun, you can see prominent differential rotation. Now, coming back to this thing, that why when the differential rotations are there and why when rigid body rotations are there. So if a star is very fastly rotating, or the star has a very high coefficient of viscosity, almost uniform in space, what happened that whenever the star tries to make some of the rotating layer to move non-uniformly with respect to the other, then there will be an transfer of angular momentum, just like linear motions due to viscosity, and then thereby killing that relative angular velocity. And if it is the case, then actually the star would display nearly very solid body rotation. Now, what happens? Let me tell you. For example, in a star, like there are, in general, for a steady state star, if the star is rotating, then like for every fluid element, or layer wise, the fluid which is rotating is subject to three type of forces. One is this centripetal force, another is like the gradient of pressure, another is the gravitational force, the self-gravity. Now, if the pressure is quite unimportant, okay, if the pressure is unimportant, that means the temperature gradient is unimportant in the system, in the star, then we can actually see that the gravitational term is somehow balanced by the centripetal acceleration. I don't know whether you have already covered the rotation, the lectures about rotation or not. You will see that once again. If this is the case, then you must have a radial dependence of the angular velocity, and that will somehow sustain the differential rotation. Now, if you consider a slowly rotating star, then for a slowly rotating star, what happens that even if the like viscosity is not very much, but it is some moderate viscosity, But what happens that one part of the pressure gradient, okay, now the pressure gradient is no longer negligible. Now one part of the pressure gradient actually balances this gravitational force, another part balances the centrifugal force. And then as a result, one can actually show that differential rotational effects are killed. Okay, so you will see that in many cases, you will have how to say, like nearly solid body rotation. So solid body rotation is not at all an idealization for fluids, but it's an observed fact. But this is achieved due to various reasons. Okay. That is one, I thought very interesting question. Then another question is weak perturbations. Okay. So theoretically speaking, it is easy to define a weak perturbation. My question is, when we are given a system where we know the perturb theory with the way forward, how do we determine if the perturbation is of first order or of higher order? Now this is it's a natural question, I agree. So the way we talk is that we first of all we know in advance by doing analytical theory that there can be two type of response in the linear theory. Okay, if you perturb the system with respect to so-called a stable configuration, then the system would produce a linear wave, or if the system is perturbed with respect to an unstable configuration, the system would either decay or the system will grow, thereby leading to a linear instability. So if these two things are prominently observed, then you can simply conclude that your perturbation is very weak and so-called first order. If you have something other, let's say nonlinear phenomena, which is not exactly like a linear mode or just like an exponential growth or something like a linear instability, then you have to think of higher order corrections. Okay, so this is very straightforward rule in physics. I can see one question by Ayush Vidyan. So just one thing, the Praveen is asking questions, sir. My aim is to create a private space company in India. So please give me, so Praveen, this course is not, and this live session is not really aimed to answer you for this type of question. Okay, so I am sorry, I will not answer to this question. I cannot. Okay, so, okay. Now, Ayush Vidlan, why the temperature gradients near the pole is less than that of near the equator in prolate spheroid? Okay. Okay. First of all, so Ayush, are you there today?
Yes, sir.
Talk to you. So your question, yes, is your question really depending on my lecture or?
Yes, sir. It's from one of your lectures.
From?
One of your lectures.
Yeah. So exactly what I said?
Just a minute. Let me just.
Yeah, please.
Yeah. So in the lecture where you talked about the effect of rotation.
I cannot hear. Okay. Mass. Yeah, your microphone is not working properly. Maybe you can type. You can type.
Okay. Sure.
Yeah. Okay. You please type. In the meantime, I will try to answer another question which was already asked. So, okay. In text 386, I don't know who this is, but he said that, sir, corona is only visible during a solar eclipse or using coronography because the particle density of the corona is quite low compared to the photosphere of the sun, so that the sun's photosphere luminosity overwhelms that of the corona, and that's why we cannot see the corona in general other than the eclipse time. Is my reasoning correct? Yes, your reasoning is totally correct. So since, just for your information, since the density of solar corona is almost 10 to the 7 times, I mean 1 by 10 to the 7 times of that of the photosphere. Okay, so you see that's a huge difference between the density of the photosphere at the solar surface and that of the solar corona. The total luminosity, that means the average rate of the radiating energy, okay, will be less. because the number of particles which are actually producing energy and can be visible due to their energy, okay, they are less in number, and that's why the brightness of corona is much less than that of the photosphere. Yeah, so you are right. Another question is okay, local Maxwellian distribution. That's a very good question. How does a local Maxwell-Boltzmann distribution differ from a global Maxwell-Boltzmann distribution? So a global Maxwell-Boltzmann distribution simply say that the fluid is at its ground state, it's an equilibrium state. Okay, so you cannot really find a, I mean, so for how to say, like the total fluid has something okay, so everything, so there is no temperature gradient, no pressure gradient, nothing. So everything is in equilibrium. So the fluid cannot actually flow. Now, if instead of that, you say that we now think of blobs of fluid which contains many kinetic particles, but with respect to a macro scale person, that means, for example, me, who can see the fluid as a continuum, this particle is still very small. Okay, then for him, if I say that I just take blobs like that, then I can just, if I assume that there is a temperature equilibrium, thermal equilibrium in that population, that simply means that you can define one single temperature, one single pressure for one fluid particle. And that actually says that finally, all the fluid particle, I mean, full fluid quantities are the macroscopic quantities. Okay. So that is the meaning of local Maxwell-Boltzmann distribution. That means the Boltzmann-Maxwell distribution and the thermal equilibrium is only for a fluid particle. Okay. So at different points in space and time, it can be different. Yes, yes.
Sir, in short, we can say
your voice is not audible. Bolo.
Sir, my question is about local Maxwellian. In short, we can say that in local Maxwellian distribution, we can treat only one molecule or one particle.
No, one fluid particle and many kinetic particles, many molecules.
One fluid particle.
One fluid particle. That means one, okay, fluid particle has a meaning is that this is the basis of the continuum. So fluid particle is, if you remember when I talked about this, developing this macroscopic equations, I said about fluid particles. Okay, so fluid particle is a, for example, is a I mean, it's a, how to say, like when you write divergence. So fluid, what is the meaning of fluid particle? Fluid particle simply means that if I travel along the continuum, then if after some delta distance, the T, this changes, then this delta will give me the size of one fluid particle.
So we can say
no, your voice is still very low. So we can say
we treat fluid particle as a ensemble in phase space. We can say that.
No. Okay, this is a different scale. Ensemble in phase space we did for kinetic theory. Ensemble, hello.
Yes, sir. Here.
Yeah. So this, and I think this part should be clear. It's okay. So once again, so once you are in kinetic theory, then so in phase space, for example, try to understand. In phase space, we are not talking about real particles. We are talking about states.
States.
Okay. For example, in phase space, one point is one state. For example, a collection of one pressure, one temperature, the values of one pressure, one temperature, like this.
Okay, sir.
Okay. Okay. Yeah.
And
But this is a good question. Huh, bolo?
In fluid particle, we can say collection of particles in which there are Maxwellian distributions.
Very good. Very good.
Homogeneous.
Very good. Very good. The minimum number of fluid particles are actually the parcel of fluid particle over which the minimum number of particles required to establish one Maxwellian distribution.
Okay.
Okay, so that is the thing. Okay,
It could be smallest possible. It could be
smallest
small.
possible. Smallest
Yeah.
possible.
Okay.
Exactly.
Thank you, sir. Thank you.
Exactly. Yeah. That's the correct one. Exactly. Good. Okay, another question. Analysis of shock wave front. This is also asked by Sumit Banerjee. We started the analysis of shock wave front by placing ourselves at the center of explosions, and then we immediately shift the frame of reference to the shock wave by applying the RH condition. That means the Rankine-Huttonio conditions. I am wondering, we could have directly started with the RH conditions. What was the purpose of studying? No. Okay. So for a shock, hello.
Excuse me, sir. Sorry to interrupt, but it will be great if you show us the questions. It will be great if you just show us the questions that you are.
Okay, the questions are all posted in the forums. So I am now. I mean, I can tell you a little bit slower, but for today I cannot because those equipments are differently done. Okay, so yeah, I can tell you the question slowly. The question simply says that whenever we are analyzing the shock conditions, the Rankine-Huttonio condition in the case of the supernova explosion, okay, then why every time we place ourselves to the rest frame of the shock? The answer is shock is something. So with respect to an observer, which is at rest with respect to the laboratory, that means with respect to a laboratory frame, a shock is moving in an undisturbed fluid. Actually, the fluid does not flow. Now, when the shock moves with some velocity, then actually only when you are sitting on the shock, then you can define flows before and after the shock. Okay, otherwise that is meaningless. That's why for doing the Rankine-Huttonio condition, always you have to place yourself on the shock. Okay. The next question is about adiabatic equation of state. It says that I am asking this question in the context of thermodynamic process. In thermodynamics, we assume quasi-equilibrium, which tells us that state variables must be changed extremely slowly so that we do not have discontinuities in the PV diagram. Here in shock waves, since the process is very fast, equilibrium or even a quasi-equilibrium state cannot be assumed. How is then the assumption of adiabatic equation of state justified? So for your kind information to all the students, this is a very, very important point. An adiabatic equation of state actually is not something exclusive to equilibrium thermodynamics. An adiabatic state is simply saying that you are isolating the system so that the system cannot exchange any heat with respect to the surrounding. Now, if after doing that, you do quasi-static thing, then you can use your normal thermodynamic equilibrium laws. If you don't do, then you have to do something else. Now, what is the advantage for an adiabatic process is, if you remember that if you even change the whole system in a nearly equilibrium way, then the first law says dq is equal to du plus dw, and dq and dw, they are not state variables. Now, if you say dq is 0, d cut q is 0, then actually du is minus dw. That means if you can maintain this d cut q is equal to 0, your du, which is a state variable, will be equal to minus d cut u, w. That means d cut w, which is an work done for an adiabatic process, it also becomes a state variable. Okay, because it is exactly equal to the minus of du. And most of the cases, the result which we will see for nearly equilibrium cases are exactly matching or very closely matching to that of an equilibrium case. However, even if you do not obey this quasi-equilibrium thing, you can still define an adiabatic process. The only thing is that your adiabatic equation of state will not simply be very close to PV to the gamma is equal to constant. But then, I mean, once again, that you can, you can do things. There is a total subject, it's called irreversible thermodynamics, and we have the way to treat those things. Okay, so here the basic approximation is that the system is the system is fast enough so that the system does not get time to exchange the heat to the surroundings. Okay, so the thermal time is much greater than the dynamic time. Okay.
Yes.
I
Can you move on?
Please.
Yes, I wrote the question in the chat. That prolate spheroids.
Okay. In the lecture named effect of rotation on a self-rotating mass, you talked about different spheroids. Yes, you did not really touch on prolate spheroids, but you gave just a little idea about how it looks. But there is a question in week 9, same as I asked, week 9 assignment. So can you now, remind me the question? I don't have the assignments, or one thing.
I wrote the question.
One thing can
I wrote
be
the
done.
question up there by the temperature.
No, one thing can be done. Please, one thing can be done. Please put that question number in the forum. Okay, and I will answer, because I don't have either these assignment questions with me. Okay, so if you, I also have one or two other questions regarding the assignments. So assignment questions, I will then try to discuss, or I don't know, just a minute. Let me ask Mr. Krishnan. Mr. Krishnan, how can I have the access to assignment questions?
Sir, shall I open it and share it right away?
Oh, sure. That will be just very kind.
Yeah, just a second, sir.
Thank you. Okay, I understand. So you guys already have done this rotation part. That's excellent. I'm just going to the rotation part so that, the instability part. This is also this part, instability.
So which assignment I should open?
So assignment 9, as far as I understand. So Ayush, can you help Mr. Krishnan?
Yeah. Assignment 9, question number 10.
Yeah, just a second.
Last question. Yeah, this one.
The question. So for a prolate spheroid, 4 options.
Okay. Now I understand. Okay. Yeah. So just a minute. First, let me just go to this rotation part. This. Okay. Yeah. So this one is this. This one is this. Astrophysical is a rotating frame, right? And then I think it's a Kelvin's vorticity theorem, Taylor-Proudman theorem, self-gravitating rotating mass. Correct. Yes. So it is then possible, right? That's true. Right, that is true too. Exactly. Yeah. Macroloid spheroids. Yeah, right. Yeah, right. Yeah. Right. Jacobi ellipsoid, rotation in the world of stars. So for a prolet spheroid, the temperature gradients near the pole just a minute. So I first have to go to this part. Yes, it's a Maclaurin spheroid. Yeah, right. So yeah. The temperature gradients. So the accepted answer is, of course, the near the pole is less than that of the equator, right? Yes. Yeah. Yeah. Okay. Yeah. Okay. In the world of stars. Yeah. Okay. So can you just? I mean, so I wish. Do you also follow the lectures?
Yes, sir, I do.
So can you go to the lecture with the title "Rotation in the World of Stars"? Because I was also not sure whether I really covered that. Yeah. So rotation in the world of stars.
Oh, rotation in stars. Okay.
The world of
I
stars.
completed that one.
You?
Just a minute.
So if you go there, so in the third slide, you will have an explanation for an oblate sphere. Okay. And you will see that the
you talked about oblate one.
Yeah. And so from that, you cannot say that you cannot really see why for an prolet sphere, the temperature gradients near the pole will be less than that of the equator. No?
So that's a open one.
See, you have to understand the gradients, where the gradients are important. Okay.
Yeah, yes, sir.
No, first of all, your microphone is. Can you just write me what is your answer? I mean. Yeah. Okay. Yeah. So please try to understand this part, because this is something not at all related to the. I mean, the part what you said. This is here actually. The thing is that you have to use another assumption. I think that is the point you maybe missed. That is that you have to use a polytropic, I mean a barotropic condition. For that, the baroclinic term actually vanishes, and that's why you have to know that if you just go to the slide just before, that contours of constant p and constant rho are either parallel or they are coinciding. Okay, so and then if you just use that fact and use also something like the relation between pressure and temperature, you will simply see that for a prolet sphere, for an oblate sphere, basically usually the rotating stars, and hence the contours of equal pressure, equal density, and equal phi effective and equal temperature, all are their oblate spheres. Okay, and when they are oblate spheres, of course you I don't know, like I can draw, but I can simply try to show you. If you have an oblate sphere, then this part is the north-south direction is actually contracted with respect to the east-west direction. And so you can see that the gradient in this way, okay, so the polar gradient in this way is actually much greater, right? Because the same amount of delta will be now have to be covered in a least distance. Okay, and if you now do a prolet sphere like this, then actually the temperature gradient near the pole. So because the same amount of temperature difference, you have to be covered in a greater distance. So the gradient, that means per unit distance, will be less. That's the thing. Is this clearer or?
Oh,
No, I think it's okay. Mr. Krishnan, you can just switch this off. I think maybe. Yeah. Ayush, is it clear? Yeah. Okay. You right. Got it, sir. Okay. Very good. Okay. I will go to another question. Always by Sumit Banerjee. He said, in astronomy, there are different type of variables stars, Cepheid variables, RR LiDAR type of variables. The oscillations introduced in this chapter gives an indication of the variability of the star. Are these the same thing, or the oscillations are more general than variability? So, okay. Variability means most of the times the variability in luminosity. So, if I understand your question, I was not aware of this question before, but anyways, I'm trying to explain. So, in a sense, variability is much more general. Now, there can be many mechanisms of variability. One possible mechanism and the most popular mechanism is the stellar oscillation. Okay. And the stellar oscillations actually can be of different type, which are mostly using kappa mechanism. That means the optical density near the center of the star, near the core of the star. In general, they have much more brighter, much more prominent visibility contrast during the pulsation. And in general, the normal luminosity range is also higher. So these things are called mostly the RR LiDAR type of variables, as far as I know. I also don't know very much about RR LiDAR type of variables. On the other hand, Cepheid stars are a little bit more dimmer, okay, than this LiDAR type of. LiDAR are much more brighter. Yeah, that's all I also know. I mean, I don't know much than that. Yeah, more than that. Okay. Yeah. Okay. Then radial perturbation. Oh no, this is something okay, I think I am done with most of the questions which are really relevant for discussion. But if now you guys have some other questions, you can ask me related to the lectures mostly. Sir, it would be great if we get solutions of the questions in the assignment. Oh, that I don't know. Last year it was distributed. I don't know. So, Mr. Krishnan, can you put some light on this point?
Yes, so once the due date is over, we are supposed to release the assignment solutions as well. I will just check with the team member who is handling this particular course from our NPTEL team, sir, and then we will release the assignment solutions.
Okay, perfect. Okay, so I think Ayush, your question is addressed.
Yeah, by tomorrow, all the assignment solutions, the ones which got over, no, it will be released. So don't worry.
Okay, excellent. And also another thing is that several questions, Professor Mr. Krishnan also informed me that there are some problems in some questions, assignment questions. I already checked with my last year TA. She had already made a list and she sent me today. I will forward it to Mr. Krishnan and he will take care of that. So in the worst case, the questions will be dropped. Okay, the confusing questions, the ambiguous questions will be dropped. Okay, so no, don't worry. Yeah, so Sanket Thakkar, how can we manipulate the system or distribution? Manipulate the system or distribution? What is exactly the meaning of manipulate? That I cannot get you. Manipulate means?
Sir, I have a lot of noise around here, so there is a Navratri is here. So
no problem. Batao thoda.
So my question is about how can we treat the system into the phase space to understand the dynamic of this system and other things, properties of the system.
Okay.
And
For that, there is a entire subject called nonlinear dynamics. Okay, so if you are interested, you can contact me later. I will tell you a lot about it. So there are many ways to treat that, many ways. Okay, you can first of all treat in terms of the point of stability, the stability analysis. That means you just perturb the some state in the phase space and see whether the point is stable, unstable. If it is stable, which type of stability is there. There can be interesting points, then different type of instability, bifurcation. I mean, it's a total, you know, it's a very interesting universe. It's a total universe. So I am totally very much interested. If you are, I mean, if you ask me sometimes in a mail or something, I will be suggesting you some study material on that. Okay.
Sir,
Yeah.
my future topic is all in about accretion disk formation. I also studying general relativity, so I want to know about different turbulence, instability in there. So can you guide me as well about?
Yes, of course, I can guide you. Write me an email and just tell me that I am a student of your NPTEL course. Okay, so and exactly ask me the question which exactly you want. So I can send you a name of a book. I can send you some study material. Already you will have some. I think you already had some introduction to turbulence in this lecture. So that you can use that. And then of course I can suggest you books. Just write me an email. I will answer you.
Okay, sir. Okay, sir. Sir, I will mail you.
Yeah, sure. Sir, those only show the answer. Okay, yeah. Okay, that's not for me. Sir, those PDFs don't really have solutions. That doesn't really have. Okay, that is also not for me. Okay.
So,
Yeah.
there's a time.
Yeah. So Aryan, yeah. Sure. Okay, yeah.
So I was talking about the synchrotron shock model, right?
Yeah.
And right. So we have basically 4 phases in which the jet comes out. And when the jet starts, we like just assume there's an opening angle theta, and which is coming from the central engine. Then the first phase is.
Just a minute. Which type of jet it is? It's an extragalactic jet, or which type of jet exactly?
It can be. It's an extragalactic jet. It's basically a gamma ray burst.
Okay, so is it just the vertical one, or it's it's a vertical one? Perfect.
We are assuming a vertical one and we are also assuming many conditions like low magnetization and all that stuff.
Yeah, that's okay. Yeah.
Okay, so we take a Lorentz bulk factor and we get a relation that the cone, that theta is increasing as per 1 by the Lorentz bulk factor. My question is, the jet goes from the second phase to the third phase, reducing in its velocity.
Yes.
So the blast wave decelerates enough that the cone becomes larger than the geometric cone. Like 1 by tau becomes greater than the theta which we are taking. And the afterglow of the burst goes into the post-jet break, right? So how does that wave basically go into Newtonian phase from this high speed, what do you call, I think Blankford-Mackie solution is, I believe it's called.
So did you consider the relativistic corrections?
Yes, sir. That the Blankford-Mackie is basically the relativistic correction.
Yeah,
right?
That's why my question. Yeah, exactly. So that's okay. Yeah. So I wonder. I have to see the estimates, because otherwise exactly terms I also forget.
I actually had this conversation with Dr. Arnab Rai Chaudhary. He's also like, we'll try to find a way.
So can you ask him, because I don't know, or you can ask Pratik Sharma. Pratik is also not working with exactly. I personally work with astrophysical turbulence nowadays much more. So I have to check. So if you want that we have a conversation on that, the best thing is you can just send me in a PDF the study material so that I can have a look at the equations. I understand what you are talking on. So that's not a problem. So you just send me the PDF or something, then I will try to answer you by email. Okay, because
Okay, sure.
I understand what you are talking now. Now it is much more clearer. But to be very honest, I also totally forgot that this transition between the phases in relativistic jets. Totally forgot. Okay, totally forgot. So I have to also revise a little bit, and then also I can tell you. Okay.
Okay, sir. No problem. Thank you.
Yes. Another point is that that is one thing. Another point is that what I was trying to say. Is there any explicit time dependence, or it is the for the steady state condition? Aryan, the same question to you. Is it a steady state solution, or is there explicit time dependence there?
I think it's a dynamic thing, sir.
It's a dynamic.
Because even the shell's velocity is not steady. Like if we are to consider it steady, then the system changes.
Then I have to see the equations. Yeah, I understand. Yeah, okay. So thanks for this question. I will be personally very much interested, but maybe not for this course. I am not ready, of course, to answer your question now. But of course, I will be happy to see the material. But please send me an email. Okay.
Yes, sir, surely.
Yeah. Any other question? Any other question? So what I personally want to request all of you to register for the exams, because if you do a course and if you don't give the exam, then basically you also will not be really able to understand this, your proficiency and the way you learned. Okay, the questions will be multiple choice type of questions. Most of them will be very, very much depending on directly from the lectures and the tutorials. So don't really worry about this, but exam will be very, very important. Okay. Yeah. So, yeah.
Sir, excuse me, sir.
Yeah.
The exam registration is already closed for our course. On 16th is the last date to register, sir.
Oh, then I think, yeah. So how many registration was there this time?
I'll just check and get back to you, sir, related to it.
Okay.
Yeah. Sir, also, can I share the solution document? Because explanations are given at the end of the document. So can I share the screen and show a sample document to the students?
Who will? You?
Yeah, I will do that, sir.
Yeah, please. Yeah.
Just a second, sir.
Please.
For example, students, in the assignment 9, you can see, like 10 questions are there, and the questions that requires explanation, it is given at the end. If you scroll down the document, you can see the worked out solution. For example, question 8, question 9, the worked out solution is given. So you can refer to it. And in case if you have any doubts related to solving these things, you can write it in the forum. Hope this helps. Okay,
yeah,
sir.
I think most of the questions are really, qualitative, and it's really you see from the lecture. So these solutions are not given. Most of the numerical solutions we provided. Yeah.
Yes, sir. It is given at the
Most of the cases, the numerical and wherever some little tricks are needed, we also provided that. Yeah.
So can we expect similar questions in the exam?
That's what I said. I, in general, don't examine or don't test a student out of the things which he or she didn't learn. Rather, I want to test a student from the things which he or she had learned in the course. Okay. So if there is no more question for this thing, so yeah, of course, there will be more session. I think there will be another session, but you see, just please, if you really want me to answer your questions carefully and thoroughly, send the questions in advance. For example, the people who just asked me the question student, and I told them that no, I don't know, or I was not ready. you could simply solve this issue just by sending me the question yesterday, right? In the Google form or something. Okay, so that's your choice. If you want me to give your answer readily, then send the question in advance, because of course it's not possible for me also to like every time to answer, because most of the cases the very topical questions. Okay, so these things should be remembered next time. So please try to share the questions in forum in advance so that I can prepare myself for those questions. Okay, and also, it's a general message that if you ask the questions, then try to attend this. For example, today I explained a lot of questions for some of the students who were not present. So now I was not sure whether the real answer was really conceived by those students or not. Okay, so it's a two-way process. Huh? Okay.
Sir, could you please share your mail ID in the chat box?
My mail ID, my name, Supratik Banerjee. You just search this, Supratik Banerjee, IIT-Kanpur. The mail address will appear without any fault. You use that. sbanerjee@iitk.ac.in. Okay, but write the mail with a proper title and also giving the introduction that you are one of the students who are following my NPTEL course. Otherwise,
Yes,
sometimes I may not open because there are so many mails with this internship request, PhD request, research position request that I sometimes don't open. Okay, so
yes,
please write that request from NPTEL student. Then I will.
Okay, sir.
Okay, yeah. Okay, I think this is done for today, and thank you, Mr. Krishnan, once again for conducting this live session so successfully. And it was also a pleasure talking to the students as always. So we will conduct another one before your final exam. And yeah.
Okay, sir. Thank you so much, sir, for your valuable time. And then participants, thank you so much. We will have one more session before the examination.
Sure.
So now we will close the session.
Okay.
Okay, sir.
Thank you.
Thank you, sir.